So just for fun, I thought it would be nice to do a little bit of preview of integrals. So I have a question for you, since it doesn't look like anyone got number 1 correct. If this 9 was a 1, would you be able to do this?
Yeah.
What function would it be?
Oh, it's the
Yeah.
tangent.
It's arctangent. Yeah. So what? Okay. So we have taught you. We have taught you this semester. We've taught you arctan with just being like 1 over x squared plus 1. We didn't teach you arctan when it comes to 1 over x squared plus any number. We just did 1. But it could be any number, and it's still an arctan. So I'm going to show you a little trick right now. If you commit this to memory, that's awesome. If you have to like kind of revisit it again in BC, then you have to revisit it again in BC. But anyway, so this would normally be 4 arctan x plus c, right? Okay. So if we change the 1 back to a 9, how does this affect the answer? You have to think of this as something squared plus something squared. This 9 is the same as 3 squared. So you divide that by 3, divide that by 3, and now you've got your answer. So anyway, so that's all I was really looking for was to see if any group recognized arctan. Nobody in either class, so that's okay. It's okay. You guys aren't used to seeing it with other numbers, right? So that's all right. Okay. So the next one is a traditional U sub problem. This is the one I'm hoping most of you got. So I'm going to kind of barricade number 1 off here. Number 2, I'm going to put the U sub up here. So U is your x squared plus 9, du, 2x dx, 2 du would equal 4x dx. So we end up with this equaling the integral of 2 times 1 over u du, which is 2 ln absolute u plus c, which is 2 ln x squared plus 9 plus c. Now, I dropped the absolute value, but I didn't have to. I could have left it. Why am I allowed to drop it?
Because x squared makes it positive.
Because x squared plus 9 is always positive, right? Okay. So anyway, so that was number 2. You got it. You got it. You got it.
I took the derivative of this arrow.
Let's see. Oops. Oops. Okay. Oops. Okay. All right. Good. Good. And you would have gotten it if you had started it. Yeah. Okay. All right. That's fair. All right. Numbers 3 and 4 can be done with special case use substitution, but not easily. They're pretty tough. Now, what I saw a lot of people do in first period, and quite a few people try to do in second period, including one that's like on the board right now, is something that if I was back in the olden days, I would, like when I used to take off full credit for bad algebra, I would have written a BA with a minus whatever the problem was worth, right? Okay, because you all know that this is not true. You should all know this should make you unsettled, right? Does it make you unsettled? It should. Okay.
And then you cancel that.
And then you can, oh, you're right. I know, I didn't go far enough with it, right? Okay, this is bad algebra. You can't split up a denominator.
Wait, is it
All right. So, rather than doing a special case u sub, which actually requires multiple iterations of u substitution, whenever you have to do a u substitution and then you have to do a u substitution again, my second variable that I use instead of u, because you can't use u again because you've already used it, so then I go to double u because it's a double u substitution, right? Okay. All right. So anyway, but instead of doing that, we're going to do some algebra, but we're going to do correct algebra, right? So the algebra that I suggested to all of you that none of you did, I'm going to move this guy separate. So I suggested that you guys try dividing. Now, there are two ways to divide polynomials. One way is with synthetic division. No, it doesn't factor. A sum of squares doesn't factor unless you want to go into imaginary numbers, right? Okay, so, but it's a good try, right? I like that you're thinking outside the box. So, one way is synthetic division. Synthetic division only works when your divisor is linear, right? So you can't do synthetic. The other way is long division. People tend to not like long division of polynomials until you realize how nice it makes some of these integrals, where if you do it the u substitution way, you'd have like a whole sheet of paper of work, and if you do long division, it's like 2 steps and you're done. So let's just review long division, shall we? This is the same thing as 4x squared divided by x squared plus 9. Now, did you all do long division of numbers when you were little?
Yeah.
Yes? Okay. All right. I didn't know if they still taught that or not. There were some school districts that were talking about dropping that from curriculum. So I think they thought it was an unnecessary concept or whatever. So anyway. Okay, long division. So when you're doing long division, you think, what do I have to multiply this by to get this? 4, right? That goes up here. And then we multiply this by that 4, the whole thing. So you get 4x squared plus 36. With long division, you subtract down, right? Now, we don't have a term next to here, so we put a 0 as a placeholder. So when we subtract down, we get 0 minus 36. That's as far as we can go, right? We don't want to try to push this into there. So we stop, and now we're ready to rewrite our integral. So this, what does this equal? It equals 4 plus the remainder, that's the remainder, over the divisor. That would be a correct rewrite of the problem, right? You guys, didn't you do long division?
Yeah.
Okay, all right, okay, but you did it. Okay, all right, that was ancient, like 2 whole years ago? All right, okay, what's the antiderivative of 4? 4x. So this guy right here is exactly the same as that guy up there. So yeah, but at least you could get to here, right? Minus 36 arctan x plus c, and then since there's a 9 and not a 1, you got to divide by its square root. So this you could rewrite as 12. Anyway, so that's long division, right? It's not bad, right?
Were you expecting any of us to figure that out?
I was you know what I honestly was hoping for? I was hoping for at least a couple groups to have the word arctan on their board somewhere, right? I thought every group would get number 2. And then I was hoping deep down that at least one group would have a rewrite. That's what I was hoping for. So, anyway. All right. So, last one. All right. Last one, another little long division. So you have x squared plus 9 going into 4x cubed. What do I have to multiply this first term? You always just look at the first terms. What do I have to multiply this by to get this? 4x. 4x. Now I distribute the 4x times the whole divisor. So I get 4x cubed plus 36x. I have to subtract. I need a placeholder, so I'm going to put 0x because I have 0 x's on that guy. Subtract down, I get 0 minus 36x. X squared can't go into 36x with multiplication. You'd have to divide, but so we're done, right? That's our remainder. So now, if I rewrite my integral, it becomes 4x minus 36x over x squared plus 9 dx. Now the antiderivative of 4x, that's easy. That's 2x squared. This guy right here is exactly the same as this guy right here, right? Instead of a 4x, you have a 36. So all you have to do is multiply whatever answer you got times 9, right? So 18 ln x squared plus 9, so minus 18 ln x squared plus 9 plus c. Done. Kind of fun, right? Sure. See how that difference, like just that little degree on top makes such a huge difference in the answers, right? Isn't that crazy? Yeah.
Can you explain the elements?
This last one or this one?
The last one.
Oh, well, the last problem is this right here, this negative 36x over x squared plus 9, is the exact same as this, just times with a negative 9 multiplied. So I just took the answer to this and multiplied it by negative 9. So, just to save time. All right, now, do I expect you to do this like today?
Yes.
Is this on your test?
Yeah.
No. This is not on this test. This is just kind of a, hey, let's see what you remember and let's see what you might be able to do kind of a thing, right? So anyway, all right. But inverse trig and natural logs will certainly be on your final, right? So you need to know those. I don't know if there's any, I really don't think there's any long division. But you never know. You know, anything's fair game. But I don't think so. All right, so today we're doing section 9.2b, which is called Euler's method. It's not Euler. Did you ever have a math teacher that called him Euler? You did not. His first name was Leonard. You called Lenny?
I like that. I think that's better. I think Lenny's method sounds much better.
Yep, Lenny's method.
That's much
All right. All right, 9.2b, Euler's method. Or Lenny's. Yes.
Lenny's method is
All right. So you don't have to write anything on this screen. This is just kind of an intro to what we're about to get into. So yesterday we started the lesson with this differential equation, y prime equals x plus y. We're going to focus on the same differential equation again today. This is a differential equation that is unsolvable analytically, unless, like, you guys, someday you could be the ones, right, to solve it. But anyway, so unsolvable analytically. Yesterday what we did was but you know all the slopes, right? You know y prime, those are the slopes. So yesterday we sketched the slope field, and then if we wanted to know the solution that passes through the point 0, 1, we just sketch a sketch of the solution through the slope field, and we get a reasonable, visual of what the solution looks like that passes through that point. So yesterday we used slope fields to get a visual representation of the solution to that differential equation. Today, we're going to use Euler's method to approximate y values on the solution to the differential equation. So here's what Euler said. Okay, we're done. All right, so Euler said, all right, you just so you know, whenever you have a differential equation, you always have a point, at least a point. There has to be at least one piece of data out there that you know, or otherwise, like, why do you even have the differential equation? So you've got a point. So in this case, we have the point 0, 1. So we have a point, and we know the slope, right? We don't know the solution, but we know the slope. When we have a point and we have a slope, what can we find? We can find the equation of a line, right? So Euler said, all right, you've got a point, you've got a slope. Let's find the equation of that tangent line, the line tangent to the solution at the point 0, 1. So we've got a tangent line. Now, we know from earlier in this semester that if we are around numbers that are kind of close to the point of tangency, that our tangent line is actually a decent approximation for the actual function, right? And we could just stick with that. But the tangent line doesn't work so hot when you get farther and farther away. This is only at x equals 1, and we're already this far away from the actual solution, right? So as you get further and further away from the point of tangency, your tangent line kind of stops being so good. So what Euler said was, but we know all the slopes, right? We don't know points, but we know all the slopes. So what if we went a little ways out and found the slope again at that new point and like just took off from our tangent line and found a new line with the new slope? And then we could just kind of keep doing this, right? Find the slope at each of those x values. We don't have the y values, but we just use the y value from our previous line, right? And just take off with a new slope, and then use the y value from the previous line and just take off with another new slope. And what you end up with is a mediocre approximation to the solution, right? So, and a giraffe. Now, the giraffe is there because in my PowerPoint, the giraffe is a hyperlink to a visual. So, okay. So I'm just going to show you a few things here. All right. So here we have, this is not the same function, but here we have a solution curve. When you're using Euler's method, there are two parameters to consider, right? So one is how many times are you going to do it? How far out are you going to go? And how far apart are you going to make your steps before you find a new slope and get a new little line, right? So I have to do it on here because it didn't work too well with my fingers. So if we make the steps far apart, then, I don't know if it'll let me drag it now. It's not going to. Anyway, if we make the steps farther apart, the solution curve, like our approximation, kind of gets a little bit further away from the curve. If we make the steps closer together, then our approximation ends up becoming better and better, right? Closer and closer to the actual curve. So this is the difference from each one x value to the next. This would be like how many times we go out, right? So anyway, yeah, so we could get like really good if we make our steps really small. Now, why do they call the step size h? So from day one in this class, we have talked about how delta x and h can be used interchangeably. H is called h because it represents the height of a rectangle turned sideways, right? It's the difference between those the x values, right? When you're doing a rectangle approximation, delta x means literally change in x, right? So I've seen Euler's method where people call it h, and I've seen Euler's method where people call it delta x. It doesn't matter. Those are interchangeable. So anyway, but yeah, so h is like your how far are you going to go before you find a new slope, right? And then it's just so you know, most people call h the step size because you're taking steps, and so your step size is whatever it is. All right, so that's your little Euler visual giraffe part. All right. Okay, so you don't have to write this down either. We're almost up to a screen where you're going to write stuff. So anyway, so this is kind of just showing you how Euler figured out how to generate the formula that we're going to use, which is this. You don't have to write this whole table. I'm going to walk you through, and then you can pick and choose what you want. If you want to write the whole thing, that's okay. But really, like this is your formula for the x's. This is your formula for the y's, and then this is your formula in words. So here's what you do when you do Euler's method. So you have to be told how many iterations you're going to do and what step size you're going to use. So sometimes they convey that information in different ways. Sometimes they'll say, hey, go from x equals 0 to x equals 10 with 2 steps, and then you know your step size is 5, right? You go 5, 10, 2 steps. So it's kind of like doing your rectangle widths, right? So sometimes they'll tell you how many steps and then where to start and where to end. Sometimes they'll tell you, hey, go from 0 to 5 with a step size of 1, and then you know you're going 1, 2, 3, 4, 5, right? So anyway, but just remember h in these formulas, h is your step size, whatever it is. Usually the step size is either a fourth or a half. Sometimes it's 1, which is really nice. It's usually either 0.25 or 0.5. But sometimes it's 1. Just so you know, the College Board, these are almost always no calculator questions. But the ones we're going to do, the first couple, we're going to use calculators. So we're going to do a couple of each so you can see. So here's what this means. So whenever you do these problems, I promise you there are other ways to do it, but they're so long and so cumbersome. The table really is your best bet. When you're making your table, the first thing you want to do is your x's. So you'll have a starting x, and then you just add step sizes until you get to the ending x. So like if I'm going from 0 to 1 with a step size of a fourth, then I would go 0 and a fourth and a half and 3/4 and 1, and then I would stop. You just walk by step sizes. So you just keep adding h until you hit your ending x value. Y is the part that takes a little bit of memorizing. This I want you to just memorize. I can show you how to derive it. It's not hard to learn how to derive. The first couple years I taught this, we derived the whole thing. All it is finding the equations of lines, right? And then finding new point, new slope, new equation of a line, new point, new slope, new equation. But it's so cumbersome. It takes so long, it takes so much space on paper that I stopped doing that and just said, you know what, just memorize. It's just faster. So anyway, so here's your formula for finding your y's. So this is our starting y sub 0, your initial y. The next y is the previous y plus your step size times your derivative evaluated at the previous x and y. So the new y is the previous y plus the step size times your derivative evaluated at the previous point. So I wrote it in words here. New y equals previous y plus the step size times y prime evaluated at the previous x and y. Do you guys need another minute? I can't tell. Yes? Okay. So much. Really? Or would it help you relax and be slightly a distraction? All right. Why can't I go forward? There we go. Okay. Sorry to distract you. Okay. So here's what we're going to do. So we're going to use Euler's method with a step size of 0.25 to approximate y values from x equals 0 to x equals 1 for the same differential equation we've been using for the last 2 days, starting with a point of 0, 1. So when I do Euler's method, my advice to you is your x part of your table can be really skinny. It's just numbers. Your y part, you're going to need a little space. So kind of keep the x's over to the left and give your y lots of space. Yes, Katya. Yes. Euler's method, there's no way to ask it without using the words use Euler's method. So even on the AP exam, it'll always say use Euler's method, and then they will give you whatever information you need to use Euler's method. Okay, so our first thing that we write is the given point, right? We're starting at the point 0, 1. Then you want to fill in your x's first. So I think I'm going to need one more. Our step size is 0.25. So what would our next x be? 0.25. What would be the next x? 0.5 or half. What's the next one? 0.75. And what's the last one? 1. And then that's where you stop because they said go from 0 to 1. So for your x's, you just sit there and add step sizes until you get to your ending one. All right. All right. Let's do the y's. Your new y is equal to your previous y, so you bring the previous y down, plus the step size times your derivative evaluated at the previous x and y. So you plug in the previous point into your derivative equation. So new y equals previous y plus your step size times y prime of the previous points, the previous x and y. All right, so this ends up totaling to what? 1.25. All right, let's do one more together. New y equals the previous y, 1.25, plus the step size times the derivative evaluated at the previous x and y. Previous x and y. So here's the thing. For the next couple examples in your homework, absolutely you're going to want to use a calculator. For the AP exam, 99% of the time these are no calculator, but 99% of the time they only ask you for 2 steps and they're usually pretty easy. The reason for that is because there's so many Euler's method programs that are easily downloadable onto a calculator, and they know that. So they don't want you to use your Euler's method program where it just says enter the starting x, enter the ending x, enter the step size, bam, there's your thing. Yeah, so instead they want you to be able to do it by hand. So the College Board is almost always going to give you no calculator questions for Euler, but your book tonight, you're really going to want to use a calculator. Yes?
Wait, so is y prime, is that just the step size?
No, your step size is this. That's called h.
Oh.
Okay? Y prime is your differential equation, right? And so when you're doing your, let's walk through it again. So previous y plus the step size times y prime, where what do you plug into it? Your previous x and y. You plug into y prime.
Oh, so 0 plus 1.
0 plus 1.
Oh.
So then for the next line, you bring the previous y down, previous y, plus the step size times y prime, which is x plus y, evaluated at the previous x and y.
So if you mess one up, you're screwed.
Yeah, it's recursive. If you miss one, you're screwed. Yeah. Yep. All right. I don't know what this is. So let's see. All right. So I got 1.625. All right. Go ahead and see if you can get the next two. Try the next two.
You know, building a nuclear bomb is that hard.
What?
All the steps.
Did you just start a sentence with building a nuclear bomb isn't that hard?
He was talking about how this isn't hard to just follow the steps. You can say about anything.
That is, yeah, you could.
It's not really steps.
Oh yeah.
So many times.
All right, 2.882. I can't read. Wait. Is that an 8-1?
Yeah, 8.125.
Okay. All right.
Yeah.
All right. Any questions on Euler? You ready to try one on your own? Start to finish? Okay.
Wait, so is this all you have to do?
Yeah. Yeah.
And then you like if they ask you to graph it.
They'll never ask you to graph an Euler approximation. Yeah. Yeah, sorry.
Is this where you're going to be like, yeah, now you have to do it because it's been...
No. Nope, you're just done. This is it. As a matter of fact, this is more complicated. The hardest problem with an Euler method ever on the AP exam is 2 steps. The only time I ever saw the College Board do something funky with Euler, and so this is 50 years of AP exams, and they've been asking it the whole time, right? One time, 1 year, they had you do it backwards. They gave you the ending number and asked for the beginning number. 2 steps. It wasn't like, 4 steps. 2 steps, simple numbers. So anyway, there was one time where they had you do that, but it really wasn't that bad. The step size was 1. The numbers were real easy if you could figure it out. Okay. All right. So anyway, no, this is not a problem yet. This is just your book showing you. So we just approximated y of 1 using a step size of 0.25. If you make your step size smaller, the smaller the step size, the closer the y values get to the actual value, right, on the function. So if I asked you, hey, what would be a really good approximation for the solution at x equals 1, it would be 3.43. It would be a really good approximation. So you can get even smaller. Like you could do a step size of 0.0001. if you wanted to, but then you're doing 1,000 iterations of Euler, and so you would probably want to use a program to do it, right? So anyway, all right, okay. All right, so you try, use Euler's method to approximate y, you'll definitely want a calculator for this. Y prime equals ln of x times y. Notice it's not x plus y, it's x times y. Your differential equation is ln of xy. If y of 1 equals 2 and h is 0.2 using 5 steps. Yeah.
Can you just like take the limit as it approaches on the step size or just 0? Yeah, exactly.
And you just get the exact function.
You still have to calculate all those points. Like, we're not on a function. We're just calculating a bunch of the individual point values. So it's not gonna generate the point values by taking that limit because you don't have a function.
Yeah.
Right? You have a function, it's recursively defined. So that's your problem. Yes.
Is this from 1 to 1.8 or 1 to 2? It's 5 steps.
Oh, good question. It's from 1 to 2. Yeah, 5 steps, meaning the initial value is your step 0. And then you go through 5 steps. So 5 iterations of Euler. You can do this. I'll even give you the first one. Here's the first one. There you go. You're welcome. Okay, so any questions? How did you do on your iterations of Euler? Excellent. Rashmi, you're good?
Yeah.
Yes? Can you see from back there okay?
Yeah, kind of. The blue numbers like
Are they a little hard? I'm sorry. Here, wait. Maybe I can do this. I made them a little bigger. Can you see that a little better?
yeah, that's good.
Okay. All right. So I have another example. I don't think we're going to do it. Instead, I think I'd like to do an AP problem. But just know, watch out. So we tried. Miss Grunwald wrote this homework. Like she's done all the homework assignments for chapter 9. And I know the book had problems, honest to God, where you were doing 25 iterations of Euler's method, right? I'm almost positive she did not pick those. So I think there might be one where you have to do 10. I know there's at least one where you have to do 5, but anyway,
Okay, I can do 5.
that's okay. So in this problem, this is kind of similar to a book question where it's saying you're going to do Euler's method. There's your differential equation. There's your starting point, right? You're going from 0 to 1. They're going to have you do it twice. Once with a step size of 0.5. That's just 2 iterations, right? That's easy peasy. And then once with a step size of 0.25, which is just 4 iterations, right? So just know that you might be doing the same problem a couple of times in your homework to compare how much better the approximation is with more iterations. So anyway, for this one, when you do it with 2 iterations, you get 2.25. When you do it with 4 iterations, you get 2.355, which is closer to the actual solution. So this would be a differential equation that you could actually solve, but not yet. Tomorrow. Tomorrow's a big day. Don't be absent tomorrow. Okay? All right, because tomorrow is when we're finally learning how to solve separable differential equations, right? Okay. All right, so we're going to do an AP problem. And I want this on your whiteboards, but just know the first part is going to just be a rough sketch, and that's okay. So we're going from 2008. This is problem number 6. And what I like about this problem is it's part what we did yesterday and part what we're doing today. So let me move this down. Oh, let me make this a little smaller. Okay. All right. So here's the thing. So for problem number 6, consider the logistic differential equation. Now, we have talked about logistic models briefly in the past. differential equations get used most often with population growth and exponential decay. Radioactive decay, population growth, some banking applications. So anyway, anything that follows any type of an exponential model. Now, populations, for the most part, do not get to grow to infinity, right? Like, there's no way that the Earth would support infinitely many people on it, right? Just like space-wise, it wouldn't work, right? Much less with resources and everything else. So, and we'd all just kill each other anyway. So instead, there's instead most like populations. There's usually some sort of like a limiting factor that is like this maximum population that your world or whatever you have can support, right? So that's what a logistic model follows. Is they end up having this line right here at what's called the carrying capacity. And what that means is this is like the highest population that can be supported with space and resources and everything else. So, for whatever you're talking about. If your population happens to start above the carrying capacity, then it gets pulled down to the carrying capacity. If your population starts below the carrying capacity, then it ends up like rising up, but then it levels off at the carrying capacity, right? This is what we're going to be studying on Thursday. Our very last lesson of AB is logistic growth models, right? Anyway, so this is a logistic differential equation. Let y, and so that's it right here. dy dt equals y over 8 times 6 minus y. Let y equal f of t be the particular solution with f of 0 equals 8. So there's your given input, right? Your first data point. A slope field for this differential equation is given below. Sketch possible solution curves through the points 3, 2, they gave you a dot for it right there, and 0, 8, which they gave you a dot for it right there. It's not one solution that passes through both dots. It's a solution through this dot and a separate solution through this dot, right? Okay, so 2 solution curves. You don't have to sketch the whole slope field on your whiteboard. Just give me a rough solution curve. All right, then part B, use Euler's method starting at t equals 0 with 2 steps of equal size to approximate f of 1. All right, are you ready, set, go.
Don't do C.
And I don't know how to make it pause. Here, I'm going to freeze. Just kidding. Yeah, don't do C. You haven't learned Taylor polynomials yet.
for standing in front, so I stood in front, but then he was taking a picture, and now
Okay. So the first thing that we needed was to sketch the solutions, and you all look pretty good. Yeah. Just make sure when you sketch your solution, so 3 requirements, right? Number 1, it's got to pass through the point. Number 2, it needs to follow the trend of the slopes. And then number 3, it has to go as far as it can. And it didn't do that little curve up thing. Okay. Has to go as far as it can to the edge of the grid, right? All right. And then this one, so this one, I would start maybe down here somewhere, and come up, and then maybe go over like that. Something like that. So, yeah, it's fine. You all have fun. They're not like super picky, like if you go a little bit more curvy, right? That's fine. Whatever. All right, so that's the solution. Any questions on sketching a solution? It's not too hard, right? It's just follow the trend. Can you all see it? This girl that had an interesting, I hadn't thought of this, but she said that she has trouble visually, like looking at a slope field and seeing the solution. Yeah. So she literally, what she does is she actually like starts at the point and follows like line by line, right? And gets her graph that way, which is fun, right? Either way, you get the graph, right? So, you know, there's different degrees of how you pick up things visually. So, All right, I'm gonna leave that there. Let's do the next part, the Euler. So we have t and we have y. T starts at 0. We're going from 0 to 1. 0 to 1. Yeah, 0 to 1 with 2 steps, right? So if you're going 0 to 1 with 2 steps, what's your step size? A half, right? So since we don't have a calculator, I'm going to use fractions. So 0, we're given, it's 8. So at a half, we have 8 plus 1/2 times. So now we've got to plug an 8 into here. So if we plug in 8, we get 1 times -2, right? So -2. So you end up with 8 minus 1, which is 7. So there's your first step. And then the next step, you bring that down, 7 plus 1/2 times. Now we have to plug a 7 in there, so 7/8 times -1. Can I leave my answer like that?
Yeah.
Absolutely. Yeah, that's fine, right? If you clean it up a little bit and you get 7 minus 7/16, it's really 70 plus 42, 112 minus 7, 105/16. Yeah, okay. So, you know. Okay. But you could, this is fine, this is fine, this is fine, right? They're all fine. So just so you know, we checked the scoring guidelines in first period. There's nothing real earth-shattering. So they just counted this curve was a point, this curve was a point. They gave you a point if you attempted an Euler's method with 2 steps. That's all it says was +1 for an Euler's method with 2 steps and then a point for your answer, your final step answer.
Oh, that's very good.
So what we do, I think on your test, is I think we do like a point for each, like for the, like we check the answer. We don't like look at the table overall. We just check your y values. So anyway, yeah, that's it. That's Euler's method in a nutshell. Any questions about Euler?
Wait, this price, did you say we've been using calculator?
So, let me